You got your piece of cardboard, 30 centimeters long by 25 centimeters wide. You're making a box without a lid. Draw a picture to represent this, and then figure out what your polynomial function will be, and see if you can graph it. So, draw your picture. So when I draw the picture, I start with my cardboard box. This is 30 centimeters. This is 25 centimeters. And then we can draw the fact that we're cutting squares out of the corners, and these lengths will all be x, leaving us with an inside part. This length would be 30 minus 2x because you've cut off x from both sides, and this side will be 25 minus 2x. If we take that and then say, okay, this is my piece of cardboard flat, showing what I'm going to cut out. After I've cut it out, what is it going to look like once everything is folded up? There's our box, open box, and we can label things again. I know that this is 30 minus 2x, this is 25 minus 2x, and there's my height of x. So my volume function becomes length times width times height in no particular order. And we can graph this. So there's part A. We've created our equation. Part B, can we graph this? Well, we're going to look at this. What kind of graph is it? It's an x cubed graph, positive or negative? Well, you'll have a negative 2x times a negative 2x times an x. It'll be a positive 4x cubed graph. So its end behavior will act like a line with a positive slope. If we set our volume equal to 0 to find our x-intercepts, we get x equals 15, x equals 12.5, and x equals 0. Going to graph this, 5, 10, 15. We know that we have an x-intercept at 0, one at 12.5, and one at 15. We know that it acts like a line with a positive slope, so its end behavior would start down here, straight through, no multiplicity, straight through, straight through. Make sure you're suffering from parabolitis. And there we have our graph. Now it asks for the domain of this graph, and if we were just given the graph and asked the domain, you would say everything. X is an element of the real numbers. But we have a real life situation here. You can't cut out, and sometimes it's nice to label what these things are, right? And our x happens to be the height of our box, and our volume is right here. You can't cut out or have a negative height. You also can't cut out more than 12.5 centimeters because then you have no paper to cut out 12.5 centimeters from the other side. So if we highlight what makes sense here, only this part makes sense. So our domain for this question is x has to be between 0 and 12.5. And they would probably accept if you included the equal signs here, because technically, if you wanted to, you could not cut anything out and have a volume of 0 and be like a really useless thing to carry stuff in. But it is still possible. But anything outside of that is no longer possible to do. And we want to find this maximum. So once again, this picture helps us to set up our graphing calculator. We can go to our calculator. We can type in our equation. And now when we go to graph this, we're going to want to see our window from probably -5 to 15 on our x-axis. To figure out how high we want to go on our y-axis, we're going to go to our table of values. But when we go to our table of values, we see that from our previous question, we already went up to 29. I had one student once see how high he could hit the down button to till the end of class, and he got to like 10,000 or something. Now it was frustrating because when he got to the next question, he had to get back to 0. So he just spent 15 minutes getting down to 10,000. He needed to spend 15 minutes to get back to 0, but there's a shortcut. So I let him get back to about 500 before I showed him the shortcut. The shortcut you can do is if you go second table set, where would you like your table to start at? I'm going to start it at 0 again. And then when I go back to my table, it's starting at 0. So second and graph to get to your table of values. And so from my table of values, I can already see that it's getting up to 1,500 and then starting to go back down again. So second table set, which is above the window button, and just change that back to 0. So now when I go to my window, for my x values, I wanted to see up to 15. For my y values, I wanted to see up to 1,500. So maybe I'll put in 2,000. And now when I graph it, I get a window that matches what I have, which is nice. And now we can go second calculate to find our maximum. And again, you can use left and right, but there's a shortcut for that as well. So right now, I can see the maximum was around 5. So a number to the left of 5, that would be definitely to the left. Maybe I'll go 3. I can even see from my diagram that when I push 3, sure enough, that's to the left of my maximum. And instead of hitting over 18 times to get past it, I'm going to say it looks like 8 is definitely to the right of it. Yeah, I went quite a bit to the right, but that's okay. And once I have those two values, push enter again, it will find the maximum between them. Drag your calculator to notes. And the question says, find the max volume to the nearest centimeter cubed. So that will be 1512 centimeters cubed. Need to make sure in all of these word problem questions we include our units. And to the nearest tenth, our x value is 4.5 centimeters. That's our height. The question also asks for the dimensions. The dimensions are 4.5 centimeters by 30 minus 4.5 times 2, 21 centimeters by 16 centimeters. So what I did is I plugged that 4.5 for x back into my diagram to see what all of my dimensions would be. 30 minus 9, 21, 25 minus 9, 16. And we get all of our answers. Questions for practice 3, 4, 5, 6. 9 and 10.